Welcome to another deep dive. This time we're tackling pattern recognition and machine learning.
Sounds like fun.
We've got excerpts from a textbook, as well as some academic papers, and we're going to try to get to the core concepts here. Give the listener a feel for the math involved.
Okay.
And also see how these techniques are used in the real world.
Cool.
So I guess we could just jump right in. I noticed that the textbook, from the very beginning, it throws a lot of kind of intense notation at the reader. Like we see things like GXOFX and, XFXY.
Right.
And it can be a little intimidating for somebody just starting out. Do these symbols actually make things easier? Or are they just meant to, kind of make it more complicated?
No, they really do simplify things, I think. It's kind of like learning a new language. Once you learn the alphabet and you get used to the symbols, then you can read, quite complicated mathematical expressions pretty easily. So like that first one you mentioned there, like the GSOFSX, that's just telling you how, how functions behave as their inputs get really large.
Okay.
So it's basically saying these two functions, they grow at roughly the same rate.
So like if you were comparing the efficiency of two, like sorting algorithms or something.
Exactly.
That notation could help you to see which one's going to work better.
Exactly.
For a larger data set or something like that.
Yeah. And then the second one you mentioned, the XXY, that's just a way of expressing the average value of a function when you've got some random variables involved. So that's kind of, a core concept in probability and statistics.
Yeah.
And pops up all over machine learning as well.
Interesting. Now, I noticed that both the textbook and the papers, they seem to really like using Gaussian distributions.
Yeah.
Like they're everywhere. Also called normal distributions.
Yeah.
Is there something special about them, or are they just kind of the go-to example?
Yeah. They are quite common. There's a good reason for that, I think. Gaussian distributions have some really nice mathematical properties that make them very easy to work with. And they often provide a decent approximation to real-world phenomena. Mm-hmm. So if you think about like heights and weights of people in a population, or like the errors you might get if you make a bunch of measurements of something.
Right.
These kinds of things often look a bit like a bell curve, which is the characteristic shape of a Gaussian distribution.
Mm-hmm. But the source material hints that Gaussian distributions aren't always the perfect fit.
Right.
So what happens when we're dealing with, more complex patterns?
Yeah, that's a good point. So Gaussians can be a little bit too rigid. If you're trying to model something like, the distribution of income, for example, you often find that it's got a long tail, meaning there's some people with very high incomes.
Right.
And a Gaussian distribution might not capture that very well.
Okay.
Another limitation is that they're inherently unimodal.
Meaning?
They can only represent distributions with a single peak.
Mm-hmm.
So if your data has multiple peaks, then you're going to need a different tool for the job. Right.
So it's all about choosing the right tool.
Exactly.
Okay. Now, I also noticed that overfitting and sparse models, these terms come up quite a bit.
Yeah.
It kind of sounds like a cautionary tale about building models that are too complex.
Yeah, I guess you could say that. Think about it this way. Like, imagine you're trying to learn a new language.
Okay.
But you only have a very small set of phrases to work with.
Right.
You might be able to memorize those phrases perfectly, but then when you encounter anything outside that very limited set, you're not going to know what to do.
You're going to be lost.
And that's basically overfitting in a nutshell. In machine learning, if you have a model with too many parameters, it can basically just memorize the training data.
Oh, okay.
But then it fails to generalize to new examples.
Yeah, it's like it's learned the phrases, but not the language.
Exactly.
All right. So how do we prevent our models from becoming these, phrase memorizing robots and get them to actually understand the language?
Yeah. So one common approach is to encourage sparsity in our models.
Okay.
So what we want is, models that focus on the most important features and ignore all the kind of irrelevant stuff.
Right. Get rid of the noise.
Yeah, exactly. It's kind of like, decluttering your mind.
Okay.
To make room for the important things. And so there are techniques like regularization, specifically weight decay, which basically penalize models that are too complex.
So we're punishing them for getting too big for their britches.
Exactly, yeah. So it's kind of like applying Occam's razor to machine learning.
Right. The simplest explanation is usually the best.
Yeah.
And that's where techniques like lasso regression and relevance vector machines come in, right?
Exactly.
I saw those mentioned as ways to achieve this sparsity.
Yeah, so lasso regression is kind of like a sculptor, who's chipping away at unnecessary features.
Okay.
And forcing some of the model parameters to be exactly 0.
Oh, okay.
So it effectively switches those features off.
It's simplifying the model.
Exactly, yeah. And then relevance vector machines, they're kind of like talent scouts, I guess.
Right.
They kind of identify the most relevant data points for making predictions.
So they're getting rid of the data that doesn't matter as much.
Exactly, yeah. And so again, this leads to a more sparse model.
Okay.
Which often provides better insights into what's going on in the data.
So we've kind of got this mathematical language down a little bit, and we've explored Gaussian distributions and this idea of sparsity. But how do we actually go from equations to, real-world actions?
Yeah, good question. So that's where the fun begins.
I like it.
Let's look at some real-world examples.
So there were a couple examples in the source material that I thought were really interesting.
Okay.
One was this robot arm kinematics problem.
Right.
And the other was analyzing the composition of, like fluids flowing through a pipeline.
Okay.
Let's start with the robots.
Sure.
So it seems like figuring out the right joint angles to make a robot arm reach a certain position, that's not always a straightforward problem.
Right.
There can actually be multiple solutions. So it's kind of like a robotic puzzle.
Yeah, exactly. Like if you think about how many ways you can position your arm to reach for a cup of coffee, for example. There are lots of different combinations of, shoulder and elbow and wrist movements that will get your hand to the same point in space.
So it's not just a simple one-to-one mapping.
Yeah.
Okay. And so is that where these mixture density networks come in?
Exactly. Yeah. So they can model these multimodal solutions.
Okay.
Which basically means, there are multiple correct answers.
So instead of just giving one solution, these networks can provide a range of possible joint configurations.
Right. Yeah. It's kind of like, having a map with multiple routes to get to your destination.
Okay.
Each with its own, advantages and disadvantages.
And that flexibility would be really useful in robotics, I imagine.
Oh, yeah. Absolutely. Like you might have, limits on how far a joint can move, or you might want to find a solution that minimizes energy consumption or something like that.
Right. Optimize it somehow.
Yeah.
Okay, that makes sense. What about the pipeline example? How can machine learning be used to figure out what's flowing through a pipeline?
Well, this is a nice example of how you can use these kind of abstract math concepts to solve real practical problems. So imagine you're trying to figure out how much oil, water, and gas is flowing through a pipeline.
Okay.
And you've got these gamma ray densicometers that are placed around the pipe, and they basically measure how much the gamma rays are attenuated as they pass through the mixture.
So it's like shining a light through a container of liquids and seeing how much light gets absorbed.
Yeah, that's a good analogy. And so by combining multiple measurements from these different densitometers, you can use machine learning techniques to actually infer the overall composition of the flow.
Wow. That's really clever. So, it's kind of like you're solving a high-tech puzzle.
Right.
You're piecing together clues from different sources to get a complete picture.
Exactly.
That's really cool. Okay. I noticed this term kernel methods popping up a few times, and also Gaussian processes.
Yeah.
They seem to take these linear models that we've been talking about to a whole new level.
Yeah, they do. So kernel methods are all about finding clever ways to transform data into a higher dimensional space. Okay.
Where linear relationships might suddenly pop out. So imagine you've got two sets of data points that are all mixed up together in some complex, non-linear way.
Right.
It's like trying to untangle two intertwined spirals. You can't do that with a straight line.
So we need to kind of unravel the data somehow.
Yeah, exactly. So kernel methods let you project the data into this higher dimensional space where those spirals might suddenly become separable.
Okay.
By a simple linear boundary. It's like taking a tangled mess of yarn and spreading it out on a big table.
Okay.
And suddenly you can see the individual strands and how they're connected.
Right. But are we actually calculating those transformations in this higher dimensional space? That seems like it would be computationally expensive.
Yeah, so that's the beauty of what's called the kernel trick.
Okay.
You can actually compute the similarity between points in that higher dimensional space without explicitly visiting it.
So we're taking a shortcut. Yeah, exactly. And that makes these kernel methods computationally feasible, even for very complex data sets.
Right. And how do Gaussian processes fit into this picture?
So a Gaussian process kind of takes the idea of kernel methods a step further.
Okay.
It's like this powerful engine that allows you to make predictions and model uncertainty over entire functions.
Okay.
Not just individual data points. So imagine you're, tracking the trajectory of a rocket, for example. A Gaussian process could model that rocket's path.
Okay.
Taking into account, the noise in your measurements and even giving you confidence intervals around its predictions.
Wow. So we're not just predicting individual points, we're actually modeling the entire trajectory.
Exactly.
And the uncertainty involved. It's amazing. Okay. There's another concept that keeps popping up, and that is this Bayesian perspective.
Right.
And Bayes' theorem. It seems like a different way of thinking about models and data.
Yeah, it is. So Bayesian inference is this powerful framework for updating your beliefs as you get more data.
Okay.
It's like you have some prior belief about the world, and then you refine that belief as you gather more evidence.
Right.
And so Bayes' theorem provides this mathematical recipe for combining your prior knowledge with new evidence to get this posterior belief.
So it's like starting with a rough sketch and then adding more details and refining the picture as we get more information.
Yeah, that's a great way to put it.
Okay. And how does that apply to machine learning?
Well, it allows you to handle uncertainty in a very natural and principled way.
Okay.
And it also provides a way to compare different models based on the evidence they provide, rather than just looking at their accuracy.
So instead of just picking the model that, has the highest accuracy on some test set,
Right.
we can actually look at the strength of the evidence supporting each model.
Exactly. Yeah.
Okay, that seems much more robust. There were also mentions of type 2 maximum likelihood and evidence approximation.
Yeah.
What are those all about?
So those are techniques for handling uncertainty and also for choosing the right level of complexity for your model.
Okay.
So imagine you're trying to decide between a simple linear model and a more complex non-linear model.
Okay.
The evidence approximation can help you determine which model is actually more likely to generalize well to new data, even if they have similar performance on the training set.
So it's like you have two different explanations for some phenomenon.
Right.
You want to pick the one that's not only accurate but also kind of the simplest one.
Yeah, exactly.
The most parsimonious.
Yeah. Okay.
Okay. So it's all about finding that sweet spot between simplicity and flexibility.
Right.
And making sure our models aren't just memorizing the data, but actually capturing, the underlying patterns.
Yeah.
This has been great. We've gone from, the nuts and bolts of mathematical notation to, this big picture of model selection and these challenges of real-world applications.
Right.
It feels like we've covered a lot of ground.
Yeah, we have. And there's still more. There's this whole other world of machine learning that we haven't even touched on yet, which is unsupervised learning.
Okay, so we've spent a lot of time talking about supervised learning.
Right.
Where we have these labeled data sets. And, we have a specific goal in mind. We're trying to predict some target variable.
Right.
But what happens when we don't have those labels? What if we just have like a ton of data and we want to discover some hidden patterns or structure?
Yeah, so that's where unsupervised learning comes in.
Okay. So it's like we're exploring a new continent without a map.
Exactly.
We're just trying to see what's out there.
Yeah. You let the data guide you. You're looking for clues and patterns without any sort of preconceived notions about what you might find.
I like it. So I saw that clustering is mentioned quite a bit.
Yeah.
As a key technique in unsupervised learning.
Yeah.
It sounds pretty, straightforward. You group similar things together.
Right.
But how do we actually, do that in a systematic way?
Well, there are lots of different algorithms for doing that. One of the simplest and most widely used is called k-means clustering.
Okay.
So imagine you have a scatter plot of data points.
Okay.
K-means tries to find k clusters, or groups by minimizing the distance between the points in each cluster and the center of that cluster.
So it's like finding the center of gravity for each group.
Yeah, that's a good way to think about it. And then it assigns points to the group whose center they're closest to.
Okay. And so it keeps doing that until it finds the best solution.
Yeah, so it's an iterative process.
Right.
So it assigns points, updates the centers, and then it keeps going until it finds a stable configuration where the points within each cluster are as close as possible.
That makes sense. But how do we choose the right number of clusters? Like, how do we know what K should be?
Yeah, that's a good question. And there's no easy answer.
It seems like that could really change the results that you get.
But yeah. So often it involves a combination of looking at the data, trying different values of K, and maybe using some heuristics or statistical measures to assess how good the clusters are.
Okay. So it's a little bit of an art and a little bit of a science.
Exactly.
Okay. Clustering sounds like a great way to find groups of similar items, but what about discovering more complex relationships in the data?
Yeah.
I saw these terms, dimensionality reduction and principal component analysis.
Right.
Are those related to this?
Yeah, absolutely. So dimensionality reduction is all about simplifying your data by finding a lower dimensional representation that captures the most important information.
Okay. It's like taking a high-resolution image and compressing it to a smaller file size.
Yeah, that's a good analogy.
Without losing too much detail.
Exactly. And so principal component analysis, or PCA, is one of the most popular techniques for doing this.
Okay. I can see how that would be useful because, trying to visualize data with hundreds or thousands of dimensions would just be impossible.
Exactly. Yeah. So PCA finds these directions of greatest variance in the data. So the directions along which the data is most spread out.
Okay.
And then it projects the data onto a lower dimensional space that's spanned by those directions. It's kind of like finding the principal axis of a data cloud, I guess.
Okay.
And then rotating it so that those axes align with the coordinate system.
All right. So it's like we're taking this this messy ball of yarn and carefully unraveling it to see how it's all connected.
Exactly. And sometimes when you do this, you can reveal these hidden patterns and clusters that weren't apparent in the original high dimensional space.
Wow, that's really cool. But I'm curious, how do we know if these unsupervised learning algorithms are actually finding real patterns?
Yeah, that's a really important point. And it's one of the big challenges with unsupervised learning. Evaluating the results can be a bit more subjective than with supervised learning, where you have these clear metrics like accuracy and precision.
Right.
So often we have to rely on domain expertise, visualization techniques, and a combination of statistical measures to kind of get a sense of how good the results are.
So it requires a little bit more, kind of critical thinking and judgment.
Yeah.
We can't just blindly trust whatever the algorithm spits out.
Yeah, exactly. Yeah, it's really about generating insights and, raising new questions and uncovering these hidden structures that can lead to a deeper understanding of the data.
This has been a fantastic deep dive.
Yeah.
We've gone from decoding the language of math to exploring these different models and the power of kernel methods and the elegance of Bayesian inference.
Yeah.
And now this exciting world of unsupervised learning. I feel like I've learned a ton.
Yeah, me too. It's been a really fun journey. And remember, this is just the beginning. Machine learning is a constantly evolving field, so there are always new algorithms and techniques and applications coming out.
So what are you saying? We should do another deep dive sometime soon.
Definitely.
All right. Well, that brings us to the end of our deep dive into pattern recognition and machine learning. We hope you've enjoyed the journey. Be sure to check out the show notes for links to all the source material and some other resources as well. And until next time, keep on learning.